Have you ever wondered where interstellar visitors might be headed after their fleeting journey through our solar system? In recent years, astronomers have excitedly observed 3 interstellar objects, ISOs, passing through our cosmic neighborhood, sparking a surge of curiosity and research in the field of astronomy. These remarkable visitors are the mysterious Oumuamua, which made its debut in 2017. The interstellar comet known as 2I Borisov, discovered in 2019, and the recently identified 3I Atlas, anticipated to be at its closest approach to the Sun in July 2025. Recent findings indicate that 3I Atlas is likely a comet, with observations confirming that it's actively ejecting water vapor as it nears our Sun. https://1I Atlas is very actively releasing water. The detection of these objects, once only theoretical concepts, has incited tremendous interest regarding their origins, their movement, and where they might go once they exit our solar system. Understanding interstellar objects is crucial because asteroids and comets represent the primordial material left over from planetary formation. Analyzing ISOs provides insights into the environmental conditions present in other star systems without necessitating costly interstellar missions. Recently, researchers Shokruz Kakarov and Professor Abraham Loeb undertook a comprehensive analysis of these cosmic wanderers' trajectories to infer their origins and age constraints. Their research revealed that these ISOs hail from distinct regions within the Milky Way galaxy and possess ages that range from about 1 billion to several billion years. Kakarov, a graduate student in the astronomy department at Harvard University, specializes in interstellar objects and has an impressive portfolio that encompasses studies related to spacecraft trajectories, direct imaging techniques, and the behavior of dark matter from outside our galaxy. Professor Loeb holds the prestigious title of Frank B. Baird Jr. Professor of Science at Harvard University, and serves as the director of the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics. Their collaborative paper detailing these groundbreaking discoveries is currently under peer review for publication in Astronomy Astrophysics, https://SLSLSAWEB.pdf. The detection of Oumuamua ignited a paradigm shift in astronomy, validating the notion that interstellar objects exist and prompting deeper investigations into their natures. As Kakarov shared with Universe Today through email, the implications of these findings extend far beyond simply categorizing distant objects. These interstellar visitors offer priceless samples from far-off planetary systems, granting us access to comprehend the chemical structures and physical characteristics of exoplanetary materials. Additionally, they act as natural probes into the interstellar medium, offering clues to the gravitational interactions that guide the evolution of star populations over vast periods. Asteroids and comets are essentially historical artifacts from the bygone era of planetary system formation, and by studying ISOs, scientists can glean knowledge about other star systems without the need to embark on potential interstellar missions. Presently, the most feasible approach to dispatching spacecraft to adjacent star systems involves using tiny wafer-like craft propelled by laser beams, which could reach a fraction of light speed. Notable initiatives such as the Breakthrough Initiative's Starshot, https://breakthroughinitiatives.org/initiative3, and the Swarming Proxima Centauri project by the Institute for Interstellar Studies, I4IS, https://www.universetoday.com/articles.NASA selects bold proposal to swarm Proxima Centauri, showcase ambitious attempts to reach the nearest star, Proxima Centauri, within a human lifespan. However, these missions come with high financial burdens, and it could take decades before we receive any insights into the conditions present in our neighboring star systems. In contrast, as evidenced by Oumuamua, 2I Borisov, and 3I Atlas, interstellar objects frequently traverse our solar system, each presenting unique opportunities for research. Establishing the origins of each ISO serves as a vital initial step toward deciphering the diversity and movements of stellar populations throughout the Milky Way.
As highlighted by Kakarov, understanding where these interstellar objects come from provides a richer context for interpreting their physical and chemical traits. If we identify that 3I Atlas likely stems from an older stellar population, we can theorize that it has undergone different evolutionary processes compared to younger counterparts. This information sheds light on the myriad architectures of planetary systems and the conditions that allow for objects to be cast into interstellar space. Furthermore, tracing these origins aids us in recognizing potential source regions and the mechanisms by which they were ejected, whether through gravitational scattering, stellar evolution, or other dynamic processes. To achieve their goals, Kakarov and Loeb employed a series of Monte Carlo numerical simulations via the Galpot Galactic Potential Model, a sophisticated software platform designed to calculate a galaxy's gravitational potential. For each ISO, we produce 10,000 possible trajectories by examining variations in their velocity data along with systematic uncertainties related to the solar motion compared to the local standard of rest. Each trajectory was integrated over 1 billion years within the gravitational potential of the Milky Way to assess their maximum vertical movements from the galactic plane. This statistical method allows us to generate reliable estimates of their orbital characteristics, taking into account the considerable uncertainties involved in making long-term predictions about orbits. Through this methodology, they were able to retrace the trajectories of these 3 interstellar entities and correlate them with their possible stellar populations. Our analysis demonstrated that these 3 ISOs originate from diverse stellar populations, each exhibiting different ages and locations within the galaxy, Kakarov noted. Specifically, their findings indicated that 3I Atlas is the oldest at about 4.6 billion years, emerging from the Milky Way's thick disk, which is significantly thicker than the thinner portion where our Sun resides and is populated with older, lower metallicity stars. In comparison, 1I Oumuamua is relatively youthful at roughly 1 billion years, sourced from the thin disk where new stars continue to form. Meanwhile, 2I Borisov is situated between these two in age at around 1.7 billion years, originating from the thin disk as well. The diversity revealed in these findings challenges the notion that these interstellar objects are exclusively expelled from recently formed youthful systems. Looking forward, these revelations set the stage for exciting advancements driven by emerging observational infrastructures. Kakarov mentioned, the upcoming Legacy Survey of Space and Time (LSST) conducted by the Vera C. Rubin Observatory is set to substantially enhance our capacity to detect ISOs, potentially unveiling dozens of new interstellar objects each year. Additionally, missions like the European Space Agency's Comet Interceptor may enable us to capture an ISO for direct analysis. These groundbreaking facilities will pave the way for statistical inquiries into the populations of ISOs, allowing scientists to gain insights into their frequencies, distributions, and diversities across an array of stellar environments. So what do you think about the implications of these interstellar visitors? Are you eager to learn more about their origins and the secrets they may hold about our galaxy? Share your thoughts in the comments, and let's ignite a conversation.